Almost dropped it. Well, hello. How are you? I'm sorry I'm late. We had to be at the school today to take everything down off of our walls. So I just walked in the door. But this is what's happening this week. Due yesterday was Waves Inquiry Stations. Due today is the FET lab. That's the interaction. So that's wave boundary interactions. And then suggested but not required. This is a close reading. It's interesting. I find it interesting comparing the different types of waves. But if you're behind, then that's something you don't have to get through. And then on Friday is earthquakes. Page 1 and 2 are the assignment, and page 3 is the extra credit. So the page 3 is the challenging part, so it's not part of the expectation for you to do that assignment. So this is what's happening this week. In order to help prepare you for earthquakes, I want to go over types of waves today. So I want to talk about transverse and longitudinal. So before we do that, I do want to talk about wave speed. So hopefully you've gone through the FET the FET lab, the simulation, and you've been able to see what types of things affect the wave of the speed. The idea is that after doing that lab in class, we would take a look at the data that you collected, and then we would come up with the equation. So I'll do my best to get around to that. But I do have to pretty much tell you what the equation is, right? So last time we talked about simple harmonic motion, that's an oscillation, that means it's repetitive. I'm sorry, I still have my keys on from work or from school. So the things that we were looking at were in the sim are tension, frequency, and wavelength. And this is about what is it that affects wave speed. So you should have seen that when you change the frequency, the wavelength also changes, but it doesn't change your wave speed. That frequency and wavelength are inversely proportional. So if frequency goes up, wavelength goes down. If frequency goes down, then wavelength goes up. So that would mean that these would both be on the same side of the equation as a product. If they were on opposite sides, then they would be proportional. But that tells us that frequency is equal to 1 over the wavelength because they're inversely proportional. As this one goes up, this one goes down. It's not equal. I have to say proportional. That's backwards. There we go. Proportional to 1 over the wavelength. And we can also say that the wavelength, remember that's the Greek letter lambda, is proportional. And again, I put an equal, it's supposed to be proportional to the inverse of the frequency, 1 over the frequency. So in fact, wave speed is equal to F lambda. All right, so you see that if you want to know frequency, you would divide both sides by the wavelength. If you want to know wavelength, you would divide both sides by frequency. And we see this relationship here. So let's do the pyramid that we have for that. So if you want to know wavelength, you have velocity divided by frequency. If you want to know frequency, you have velocity divided by wavelength. If you want to know velocity or speed, you have frequency times wavelength. So now that leaves us with tension. And hopefully you were able to see that tension is the only thing that affects wave speed, either the tension or the medium that you're in. So if you're in water, you have a certain wave speed. If you're in steel, you have a certain wave speed. If you're talking about waves traveling through the air, you have a certain wave speed. So in fact, sound, the speed of sound in the air is 340 meters per second. So let me see what we can do about that. I have my sine wave over there. So speed of sound, so I'm doing a subscript sound, is in air is equal to 340 meters per second. So things that can change that would be temperature. So if it's colder than normal, the speed of sound will be different. If it is greater humidity or greater barometric pressure, you can have slight variations in this, but at a normal temperature in air, this is the speed of sound. So typically, unless we're given other information in a physics problem, this is what we use for speed of sound in air. Now, sound travels quicker in water. I'm sure you've listened to things when you were underwater swimming, and things sound very different, don't they? Well, that's because sound is traveling faster underwater. And then sound travels even faster in solids than it does in liquids. So the only thing I can think of, and I know no one has ever done this, but in the good old days, the old Western movies, you're out in the middle of nowhere, but there are train tracks running through the country. You cannot hear that there is a train coming, but if you put your ear to the steel train tracks, you can actually hear the vibration. If it's within a certain distance. So the sound is traveling much faster and stronger in the steel than it does through the air. Transverse waves are the first type of wave that we want to talk about. So we have the motion of the medium is at right angles to the direction of the wave motion. So that means in water, the wave is traveling this way, but the wave is going up and down, right? So that is right angles to the direction of the motion. So that would be a transverse wave. Sometimes that's called an S wave. And it's very easy to draw it like the sine wave that we did in the last lesson. So we had done an anatomy of a sine wave last time, and we can see, oh yeah, that's a sideways S, right? Here it is, S. So it's very easily represented by a sine wave. I'm going to have to get a different marker. That one's not happy. Here, I have a blue one that's working. Perpendicular, so this math symbol means perpendicular. So the motion of the medium, so that's the up-down motion of the wave in water, is perpendicular to the direction of motion of the wave. But the wave is coming into shore and going out. So the wave moves up and down, but the direction that the wave is traveling is into shore and out. If you're on a speedboat in the water making waves and the wave is moving away from the speedboat, so it's going in larger and larger half circles from where it originated. So it's the same. It's the same as shaking a rope up and down. So you have one end of the rope tied off and you shake the rope up and down. That's your S wave. Examples are stringed instruments, the surface of liquids, like we said, a water wave, and electromagnetic waves. So we won't have the opportunity to go into the electromagnetic spectrum, but that includes radio waves, light, microwaves, X-rays, gamma waves, all of that. All of those are transverse waves, and they have this motion. The motion of the wave is perpendicular to the direction that the wave is traveling. The other type of wave that we have is longitudinal. So longitudinal, that means it's moving in the same direction. So if I have a slinky on the table, I push it in and pull it out. We can see that compression of the slinks in the slinky move along the way, the slinky, and back again. So the direction of the motion of the wave is the same. It's in the same plane as the direction of that the wave is traveling. So let's see. I don't want to get rid of my sine wave that I have over here. But I have this about series and parallel from last week. So let me do this one. And I'll start with that much of it cleaned off. I'll probably get to the other side. So we have longitudinal. They're long. Longitudinal. So that's a compression wave. That can be considered a P wave. You'll see about that on Friday. And that's the same as pushing the slinky in and out. And sound is an example. So sound travels by the disturbance in the sound, in the wave, knocking into the next air molecule. And then that knocks into another air molecule and it picks up that energy. So the energy is transferred and until it reaches your ear. So there have to be air molecules there in order for the sound to travel. So in the vacuum of outer space, there's no sound. So when you're watching one of the, I don't know, Star Wars or Star Trek movies, and they're showing you all kinds of sounds happening in space during the battles, that is not realistic because there are not enough molecules in outer space to allow the vibration to go from one place to the next. They can't bump into each other. Then finally today, I want to talk about interference. So we can say that, I should put down an example of longitudinal is sound. Oops. So next we have interference. So more than one wave can exist in the same space at the same time. Those waves interfere with each other and they cause an interference pattern. So the two main types of interference that we would talk about would be constructive interference and destructive interference. So let's think about, what do you think it would mean if we're having constructive interference? What's going to be happening to the waves? Are we building them up or breaking them down? So hopefully you're thinking that if it's constructive, just like construction, you're building something, that we're talking about building up the wave. So if we have two waves that are approaching each other and they're both above equilibrium, so this one is moving this way and this one is moving toward it. So these are both above equilibrium, when they meet, they're going to build up into a bigger wave. So let's go ahead. I should have done a different color for this one. So now we're in the middle, and let's make this one the blue one. And I have red. We'll make this one the red one. So when they meet, you have that one plus this one happening. So we have to add this to this. So we end up with a wave that's twice the size of the one that we started with. And that's constructive interference. Let's see what twice is. Oh, it's going to come all the way up to here. All right, so that would be constructive interference. That means that we're building up the wave because we're adding this one to this one. That's all that we're doing. Now, the really interesting thing is that after these two waves pass each other, they go back to being their original wave. They continue in their path, and they're back to being the original wave. So after they meet, we get, that's the one that's traveling this way, and this one that's traveling that way. So this one has continued on its way. This would be the red one. I'm sorry, I should have color coded that better. There we go. So that's constructive interference. Now let's say that we have one that's above equilibrium and one that's below equilibrium. And this one is traveling, I don't know, is that to the right? And this one, oops, wrong way. We're doing destructive. This one is traveling to the left. Now, when the two of them meet, we have a high meeting a low. So if this was a positive one and this was a negative one, I hope you're seeing what that's going to look like in the end. So we have our positive and we have our negative. And if this is positive one and this is negative one, and again, my drawing is not, it's not to scale, it's not even, we get flatlined. This one totally cancels out this one. So they have canceled each other out. And again, after they pass, they continue in their path. And we get our blue one traveling to the right. That's above equilibrium. And our red one traveling to the left. That's below equilibrium. And of course, they wouldn't always be exactly the same size and shape, but the same thing would be happening. If this was smaller than the blue one, then you'll have this one broken down, so it's still destructive because it's being broken down into a smaller wave. And your constructive interference, if they were both below equilibrium, they would build up, but in the down direction instead of the up direction. That was all that I wanted to cover today. And then I'll talk a little bit about earthquakes on Friday. As far as next week, I'll have to talk with the other physics teachers. We were planning an end of year assignment for you. I'll have to talk to them and see if we're still planning that. All right, well, take care. And I guess I won't see you, but take care. Bye-bye.